How to simplify multi-phase DC-DC converter design. Have you ever wondered how to make multi-phase direct current to direct current converters easier to design? Let's break it down into manageable steps. Multi-phase converters are great because they use several power stages that work together. This helps share the current load, reduces voltage ripple, and improves how well the system manages heat. By using multiple phases, you can also use smaller inductors and capacitors, which boosts efficiency. First, think about how many phases you need. Choosing the right number is key. More phases mean less current per phase, which helps with heat and power loss. However, adding more phases can make the design more complex. A good rule of thumb is to aim for 6 or 7 phases. This keeps the current manageable while reducing ripple without needing too many components. Next, pay attention to the switching frequency. This frequency impacts the size of inductors and overall efficiency. If you go with a lower frequency, around 300,000 Hz, you will have less switching loss. But you will need larger inductors. On the other hand, higher frequencies up to 1 million Hz can improve response time and allow for smaller components, but they can also increase switching losses. Choose a frequency that meets your efficiency and size goals. Interleaving is another technique to consider. By timing the phases to switch at different times, you can reduce both input current ripple and output voltage ripple. This means you can use smaller output capacitors and inductors, simplifying the design and cutting costs. When selecting inductors, aim for a value that keeps the inductor current ripple between 20 and 40% of the maximum phase current. This balance ensures good efficiency and response. Smaller inductors can improve response time but may increase ripple, while larger inductors reduce ripple but can slow down the response. Coupled inductors are also worth considering. They can help reduce ripple and improve response by sharing magnetic flux between phases. This can lead to smaller output capacitors and better overall performance. Choosing the right power devices is essential. Look for metal-oxide-semiconductor field effect transistors with low on resistance and fast switching capabilities. Wide bandgap devices, like gallium nitride transistors, can handle higher frequencies more efficiently than traditional silicon transistors. Using integrated or modular controller solutions can also simplify your design. Controllers with built-in drivers that support multi-phase operation reduce the number of components you need. Digital controllers allow for real-time adjustments to pulse with modulation, which can improve regulation and response. Implementing pulse with modulation is the standard way to control multi-phase converters. This method adjusts the duty cycle of each phase to maintain the desired output voltage. It simplifies control algorithms and allows for precise regulation under different load conditions. Lastly, don't overlook thermal management and layout. A well-designed printed circuit board layout helps spread heat and minimizes electromagnetic interference. Keeping loop areas small can also reduce noise and improve efficiency. In practical terms, multi-phase converters are used in power systems and renewable energy applications. They are ideal for powering high-current loads like networking application, specific integrated circuits, microprocessors, and battery management systems. By reducing ripple and improving thermal performance, these converters provide efficient and reliable power delivery. Simplifying the design of multi-phase direct current to direct current converters involves balancing the number of phases, switching frequency, component choices, and control methods. By focusing on these factors, you can optimize efficiency and size while making the design process easier.